Good afternoon. My apologies for the delay in starting our this session. It so turns out that there is another course going on in the chemistry department which has a huge number of attendees who have come, and so this guest house, the kitchen, I think, was overwhelmed, because of which our lunch was also delayed. But anyway, any questions based on what we covered in the first session? Questions? Yes.
When we use technology to treat water,
Yes.
so energy in terms of means invested during the treatment process. Energy is part of the energy, means mechanical energy, or suppose we are using some chemicals. So we have to sum up, then that is the total energy.
Absolutely. That is what we do in this life cycle analysis. What are the energy inputs? What are the carbon inputs? But you have to do a full, in order to do complete budget, you have to look at all the sources of energy. Yes. Only then can you make a determination whether this is economically feasible or not. Because energy and cost are related, right? Any other question? So that's a very good question, because it leads us into our next discussion topic, which is what is the relationship between water and energy? And the term that we use is nexus, water energy nexus. And the idea is, well, when we look at energy, when we generate energy, then for that we need water. And typically, if you look at thermoelectric generation, which is by far the highest percentage, then in the United States, and this is a little old data, 2010, for thermoelectric power generation, which includes coal, oil, natural gas, and nuclear, 45% of all fresh water withdrawals in the US were for this thermoelectric power generation. So you can imagine, we are looking at huge numbers. And the predictions are that as soon as 2030, the water that is needed for electrical energy production could more than double. So you see the situation that we are in terms of that. Right now, we do have some parts of the US which are under stress in terms of their ability to give us the water that is needed. And if this happens, then this is not very far in the future. 2030 is just 12 years away. So we are looking, even in the United States, at some problem areas. And whenever we talk of energy production, we say, well, fossil fuels have all kinds of problems. So why not substitute fossil fuels with renewable energy? And the answer is partly correct, but partly not correct also, because when we talk of renewable energy, besides wind and solar, the next one in that list is biofuels. And it so happens that if you use biofuels, they need more water than even thermoelectric. And so we need to think afresh. So in terms of water reuse, these are some of the issues. I mean, when we talk of energy, there are all these different units, kilowatt hours, joules, British thermal units, terawatt hours. So this slide, we will need these numbers when we do some energy calculations, which we shall do in tutorial. The overall picture is very straightforward. To generate energy, we need water. And to treat water, we need energy. So there is this nexus. And the better we understand this nexus, the better we are able to come up with the optimal system. Okay. So whether it's thermoelectric, hydroelectric, um, hydrogen or fossil fuels, we need water. And in order to distribute water over large distances, I mean, typically in a city, you can imagine you have your water treatment plant at one location, and then either by gravity, I mean, you typically pump it to some overhead reservoir. From there, it is fed by gravity. But there are these pumping costs. And when you collect the wastewater, there is a cost, energy cost, and then to treat it. So now, when we look at treatment, then there are two things that are coming into the fore. One of them is what is called centralized treatment, which we talked about, where you collect, bring it to some central facility, and then you treat. But in many parts of the world, what is gathering more traction is this concept of decentralized treatment. Decentralized treatment also goes by the name of on-site treatment. And the idea is that rather than collecting and transporting over large distances, why don't we treat it at the source itself? And if you look at energy equivalence, for example, these are based on some typical comparisons. Well, if you do a centralized treatment, then, I mean, these numbers are not really, the unit is not very important. What is important is the relative scale. So you need 40 units of energy, let's say, 40,000. Whereas for centralized treatment, you need almost 4 times as much. So one thing we can say for sure is that decentralized treatment requires much less energy. Then if you look at how much of greenhouse gases are you emitting in terms of carbon dioxide equivalent, then if decentralized gives you, let's say, 1,900 units of carbon dioxide, centralized gives you more than 7,000. So it's a pretty appreciable difference. And in terms of cost, which is of course the final consideration, if this costs 6,000 units, this costs more than 80,000. So what I'm trying to say is that when we do source separated treatment, then we can look into on-site or decentralized treatment, and that gives us advantages in many. And so let's just take one small setup. Let's just take this small setup. You have, let's say, you are doing rainwater harvesting, and you also have potable water that is being supplied. So you use it. And now, when you have degraded its quality, if you can separate in terms of play water, which means the water from sink, the water from shower, etc., then you don't have to do much treatment because that grey water is not heavily contaminated. And you can use it for non-potable purposes. So even in the house, when we say in the house we need so many liters of water per capita per day, only a very small amount of it, only a very small percentage is needed for drinking or cooking. There are many other applications where you don't really need the potable water. So, if you can separate, grey water needs very little treatment, can be put back into the system. Yellow water, you have to, of course, treat it. And yellow water contains the nutrient ammonia or nitrogen. So, you can recover nitrogen, which we will look into not tomorrow, day after tomorrow. And black water, which is the one which is the most heavily contaminated. But in terms of the contamination, it's mainly organic contamination. So if we can harvest that carbon, we can get in. So that's the idea. but there are some challenges as well. The main challenges, main barrier that we are facing is that the adoption rate is very slow. You can see that in water treatment or wastewater treatment system, we don't want to take risks because it directly affects so many people. So whatever has been going on for a long time, we typically just want to stick with it. But now, as we just saw, because of climate change, because of pressures for fresh water, for so many reasons, we need to come up with these new technologies, but their adoption rate compared to, let's say, information technology in water treatment or in wastewater treatment, the adoption rate is much, much lower. And of course, this cannot be a top-down approach. You cannot just come up with a law that says you have to reuse more of water, because ultimately it is we, the people who are using this water. So the social component, the public education component becomes very critical. And what we have to do is to convince people through some successful demonstrations that look here in this project, this is what we achieved. And I'll go through some of them very briefly in the next session, in the next talk. Nothing really for me to highlight except this idea that when we say water, actually speaking, all of our water is reused. There is only a finite amount of water available on the planet, and it's being recycled. And so there is a very famous book on water, and the author makes this a very interesting statement that this water that I'm drinking, at one time, this was the urine of a dinosaur. And the idea being that without our knowing or without our being aware, this finite quantity of water is being recycled through the water cycle. So we cannot generate more water. All we can do is manage it. That's the idea. And as I said, I very much would have liked to include this LCA, life cycle assessment, but unfortunately we won't be able to do this by. Okay, so energy requires water. How much? Now I don't know in India. The number that we typically use in the United States is 100 gallons per person per day. This is for our design purposes. 100 gallons is about 385 liters. So in India, it's much lower. I know. I don't know how much lower. 135. Okay. So you are looking at 135 liters per person per day. But what we need to keep in mind is that much more than this, is the amount of water on a per person per day basis that is needed to generate electricity, and even more to generate the food that we consume. Okay? So this 135 liters per capita per day is the direct use, but then when we are looking at the water budget, we have to keep these other figures in mind. And the point that this slide is trying to make is that if you look at water demands by energy sector, you will see that, for example, biodiesel, which is something which is very hot in terms of research. Biodiesel, the idea being that if I can produce biodiesel, then I have a ready-made substitute for the diesel, the fossil fuel diesel, which will run out sometime soon. We don't know when. But the problem here is that the amount of water needed for biodiesel is huge. And I just want you to familiarize yourself with this unit. This unit basically means 1 million gallons. That means 4 million gallons per million watt output. That's the unit. And as you can see, biodiesel, soy for biodiesel, very high water demand. Ethanol, again, something that we have been touting as being the answer to our fossil fuel dependence. That grow corn, that generate ethanol out of it, and ethanol can be a fuel. And yes, it is. But in terms of water usage, very high. And I'll just skip the rest because they are not necessarily relevant for us. But what the point I'm trying to make is when we look at this water energy nexus, we have to keep all these things in mind. Where is our energy coming from? Where does the water for that energy come from? And then the other part of it is when we are treating water, how much energy do we use? So how much water will advanced technologies require? When we look at water demand, we know that there is spatial and temporal variability. In the monsoon season, we have a lot of water which is flowing through the rivers. In the dry season, very little. So there is all these things that we have to keep in mind. I'll just skip this for time. All right. So now let us look at some usage. Now, again, this is all US data. Approximately 13% of total US electricity is used in the water and wastewater. 13% of total electricity that's generated. Okay. And but if I look at municipalities, then 35% of energy usage is for water and wastewater. And the number is huge, $6.5 billion per year, and it is estimated to grow. So the reason being, of course, electricity generation. We are facing, even in the United States, big problem in terms of aging infrastructure. So as the infrastructure ages, it becomes less efficient. We lose. I don't know comparable numbers in India. In the United States, we lose at least 15 to 20% of the water as we try to supply because of this aging infrastructure. We have old pipes which leak. 15 to 20% is a huge loss. So this is just another way of putting that number. This is kilowatt hour per acre foot of water. That means how much energy per unit. And right now, our public water supply systems, they require very little energy. Why? Because the water is, the source typically is very good, and we need very little in terms of energy. If you look at a typical water supply scheme, as I said, coagulation, percolation, sedimentation, filtration, disinfection, they are not energy intensive. But if we go to, if the quality of the water worsens, we go to brackish, if we go to sea, then energy use is much. Especially desalination, energy use is typically about half the cost of the water production. So, yes, this question. So, we have to keep this in mind all the time. Developing new technologies, determining life cycle costs. There's nothing for me to really say. So let's look at some models that have been developed, some ideas basically. So if you look at yellow water, urine, what you can do is you can collect it, and you can, after you some treatment on it, you can use it as a liquid or dry fertilizer. We will talk about dry fertilizer in the nitrogen recovery session. If you are looking at groundwater or black water, you can do anaerobic digestion, which we will do in the next discussion. And that will give you methane, biogas, that you can then use to generate electricity. If you are looking at clay water, as I said, you need very little treatment, and you can use it for gardening, you can use it for hydroponic, you can use it for many other applications where the quality needed is not that much as is needed in drinking. And you can use it for direct groundwater recharge or directly use as well. So today we have technology where if you give me wastewater, let's say from a hostel in the 90s century, we have the technology where we take this wastewater from the NIT hostel and run a series of processes, such that at the end of it, the water that will come out is drinking water. We have the technology. And it has been used in many parts of the world. The three foremost countries that come to mind are Singapore, Australia, and Israel. They are doing this. But what many other countries are doing at a little lesser scale is that they take this wastewater, they convert it into drinking water, but they don't use it for drinking. Why? Because there's always this public perception that am I being forced to drink this water which was wastewater just a few moments ago? And public perception, however unscientific it may be, it's a very serious challenge. So what many parts of the world they are doing is they treat this water, convert it into drinking water, but they don't use it as drinking water. They just use it to recharge the ground. Because as you know, groundwater depletion is also a major issue. We pump so much out of groundwater that the natural replenishment rate, we are pumping at a much faster. So if I put this into the groundwater, then it is recharging the groundwater. And then later on, when people withdraw from the ground, when they withdraw groundwater, the public perception is that now this water has flown through some filter in the ground, and that has taken care of if there are any remaining contaminants which were not treated. So the idea being that if I have rainwater, I can use it to recharge the groundwater. If I have even black water, I can put in a treatment train whereby I can again use it to recharge the ground. And if it is organic waste, we can do composting to make a soil improvement, or we can also go through this. So this will be the overall framework under which we will operate. So let's just look at it in terms of classifications, in terms of categories. So if you're looking at water recycling, then the highest quality, of course, would be drinking water, potable water. But you may not need drinking water for all applications. What is known as flush water in the United States is water that you're using to flush your toilets, and that water, of course, does not have to be drinking water quality. So if you are using grey water, for example, you can do that. And of course, industrial water usage, it depends on the industry, of course. The idea being that many industries, they do not need drinking water. So if we can supply them water at whatever quality they want, then we are in business. Then we come to nutrient reuse, agricultural irrigation, forestry, aquaculture. Aquaculture is now becoming very important. What has happened, if you look at the worldwide fishing scenario, we have overfished. That means when you have a fish stock, it has a certain replenishment rate. If you fish now at a rate more than that, then you are depleting the stock. And so many parts of the world in the oceans, which were big fishing places, they have now generate that much more quantity of fish. So what do? And the answer to that is aquaculture. That means you grow fish in a controlled environment. That would be indoor, what is known as indoor aquaculture, or it could be in pens in the ocean. But the idea being that because you are controlling the environment, you can now reuse the water. Nutrient, of course, fertilizer, solid and liquid, which we will look at, energy, methane, which we will look at, ecosystem services like groundwater recharge, as I just described, and we now, a lot of people are doing research in what is known as upgrading the value chain. That means you take this wastewater, and this wastewater, after you do some treatment on it, you can get a protein feed that you can feed, let's say, farm animals. Now, in terms of technologies, they could be decentralized or centralized, separate gray water, and so forth. And of course, when we look at benefits, health benefits, environmental benefits, energy, food, water, these three, energy, food, and water, they become very, very important. So there are many programs now which are looking at these three things together. And benefits of investing, of course, we know that the more a society has access to sanitation or better quality water, the more benefits we get in terms of public health, environmental benefits, so forth and so on. So this does not have any number scale. Benefits are not quantified. But the idea that this OECD graph is trying to tell you is that as you go higher up in terms of these benefits, then, I mean, of course, you need more investment, that is a no-brainer. But the society reaches the more advanced level. That's what this is trying to say. Benefits for local communities. We will look at some of these. Source of income for farmers, fertilization, fertilizer, recycling of local water, reducing energy, so forth. Okay, so that completes this part. Benefit for other sectors, food security, livestock, health. If you look at the history of humanity, let's say, in the last 200 years, the rate at which it has progressed is much, much faster than, let's say, 2000 years before that. And why is that? That's because we were able to, if not eradicate, significantly reduce water-related diseases. I mean, even today, when we hear of the floods in Kerala, when we hear of a cyclone or a hurricane, which displaces a lot of people, they go to a camp. We know how important supply of clean water is. But in general, if you look at the world in total, mostly we have been able to significantly reduce these water-related diseases. And that's why our average age has advanced, and has become much higher today. And not just life expectancy, but even the quality of life. They all are related because we have much better access to potable water and wastewater treatment. So these benefits we cannot ignore. So that completes this discussion. Questions? Yes.
Will you focus a little bit on decentralized, difference between decentralized and decentralized? Much specific aspect. Because like decentralized can be of different things typically. Like this can be for small community also we say that this is decentralized. But what specifically you mean decentralized?
The technical definition of a decentralized treatment is the treatment is at source. Now, that source could be as small as an individual residence, which is what we call typically septic tank systems. So, now of course, that is a little primitive. In a typical septic tank system, that means you don't have access to a wastewater treatment plant, a sewer as we call it. You get this wastewater from your house, it comes into a septic tank. I mean, this advertisement that you see all the time, remember? Dosh Shauchalay ka ghar hoga. In one septic tank, you you apply your wastewater, and then after whatever time, 2 years or whatever, when it gets full, you just let it sit idle. You don't push any more wastewater, and that natural process generates a compost. That is kind of a little primitive. What we now typically mean by decentralized is take this wastewater, you treat it at the source, but it involves much more than just a septic. Typically, it will involve what is known as a septic tank, and then what we call as a SAS, a soil absorption system. And in the soil absorption system, we can denitrify, for example. We now have very good technologies where this water that comes out of the septic tank, if you aerate, if you have a toxic atmosphere, then you have a biomat. That means the soil has a biomat. So as this water percolates, the biomass is able to absorb or transform the organics much more. And so at the end of that process, the water that gets into the groundwater, that is much, much better. And now we have been able to go one step further. So start with the septic tank, then rather than a soil absorption system, which is what we call a passive technology, you can have active technologies, even at the scale of a residence, whereby, and I won't have the time to get into, but I can share with you some of the technologies that we have done, where you use principles of biotechnology, not only remove nitrogen and phosphorus, but also. So when we say decentralized, it's the whole slew, but the fact remains that it is treatment at the source, whereas centralized means collect, bring it to a central facility and treat it.
The centralized system is costly due to transportation of wastewater.
Mainly it is the pumping cost, but
if the diagram which you are showing, in case of centralized, we are taking the whole wastewater and we are treating it somewhere. But in case of decentralized, is it per decentralized treatment, or you are showing for the certain numbers of decentralized? Is it for one decentralized?
I mean, these are comparable numbers. I mean, these are based on what we call normalized values. That means,
because if we sum up all those things, then it will probably cost more than the centralized treatment.
No, that's not the idea. So here, when we are doing these equivalents, energy, carbon dioxide, these are all based on the same amount of water that we are drinking. Now, of course, when you have, let's say, you have a village of 100 houses, I'm just making it. You have to put in 100 decentralized units if you are doing it at the individual house level. Whereas if you collect it, you're treating it only at one place. You're collecting from 100, doing it a month. So, but if you look at the numbers, the cost for those 100 houses, decentralized still costs less. But of course, you need a much more, sophisticated infrastructure network. Because you see, the biggest problem with decentralized treatment is you have to rely on electricity. And you can say, well, in an advanced society, that shouldn't be a problem. We typically have electricity all the time. But when you're looking at it from a treatment point of view, you cannot afford even 1 hour of power cut. And so the The latest in decentralized is what we call energy neutral or energy sufficient. That means we are treating this wastewater, but we are also generating energy that is enough to run it on its own cycle, so that we do not have to rely on what we call energy from the grid. Because the moment you depend on energy from the grid, you have this problem of what happens if that supply fails. So these numbers look very favorable in terms of decentralized, but there are some other issues which I didn't go and get into detail. Which one was it?
I was wondering if
Yes.
everything is same, like in this comparative chart, then how could the kg CO2 values differ? Is it the carbon footprint of the entire?
Yes, this is the carbon footprint. I mean, when you look at, for example, centralized wastewater treatment, the biggest component in centralized wastewater treatment is electricity cost of the pumps and the flows. And as you know, electricity, more than 80% of this electricity is generated from coal and natural gas and petroleum. So there's a huge carbon footprint for that. Whereas if you do decentralized, and as I said, if you can recover some of this energy, then it's a whole different ballgame. Yes.
Sir, I have a question. Sir, can you please elaborate the technology of aquaponics using wastewater treatment?
Aquaponics. I don't know much about aquaponics except that the few aquaponics centers that I have been to, they have this capacity for reusing the water, and it all depends on what you're trying to grow. The examples that I have seen most are things like lettuce or cabbage, but in aquaponics, the biggest research question is, if you are reusing the water again and again, many cycles over, is there a chance that some trace contaminants like pesticides, like herbicides, will they get concentrated in the food that you're growing? That is the biggest question, and nobody has the definitive answer to it because it's a very complicated system. So in Israel, the research team that I know of, what they did is that they took a test bed aquaponics center and they took wastewater, they treated it, they applied it on this produce, then they collected the water, again they treated it, again they applied it, and their latest findings are that yes, some hormones or some what we call recalcitrant organics, they may have a tendency to concentrate, but as of now, the levels to which they concentrate do not constitute a health hazard. But it's a very, very difficult question to answer because what is the health hazard we don't know. Because typically what happens when you look at the health effects, it takes generations before the health effects are really manifested. So what is the safe concentration of, let's say, a pharmaceutical? Now, the problem that we are having now with wastewater is that the concentration of pharmaceuticals and personal care products, we call them PPCPs, the shampoo, the kind of medications that we take, their concentrations in the water are rising. And what is the safe concentration of tetracycline in the water that I drink? Of course, it is the nanograms per level, right? But what is the safe concentration? I think it's impossible to answer. It's impossible to answer because when we look at health effects, what do we typically do? We typically take a lab animal like a guinea pig or a rat, and we feed them much higher levels. And then we see, okay, at what level do you see increased cancer risk? And so if it comes out, let's say 500 units, we say, well, then multiplied or divided by 100 to move from animal to human, and then again another 100 to move from kind of get to categories like infants and old. So the idea is, if you see in a rat tetracycline at, let's say, 500 units, then we will say for humans it will be 500 divided by 100, which is 5, divided by 100, which is 0.0. But that is also very problematic. How can you say that 0.05 is safe? Because when we look at cancer, for example, in cancer there is no such thing as safe and unsafe. It's a linear line. And so even if it is 0.05, there will be a response. Now, the question is that response in a million population, how many people have that elevated response? And the typical answer is, well, if it is less than 1 in a million, we are okay with that question. So, but that 1 in a million is also very problematic. So to answer your question, in aquaponics, the potential for water use is much higher than in some other. And it has been used in many parts of the world, especially in countries like, what comes to mind is South American countries like Ecuador, Bolivia, where they grow huge amount of flowers. Today, when I read it, I was also very surprised. Most of the flowers that you buy in Europe, they actually come from Central and South America. And so these huge, you can say, flower producing factories, these are greenhouses, but they are basically factories. They have a very good potential for water use, because in order for you to be competitive, you have to use the water. Because if it is once through, as we call it, you take water from a river, you use it to grow flowers, and you discharge the water to the river. Cost is not. Because, I mean, the biggest problem in our field is that people do not know what is the cost of water, or they are not willing to pay. I mean, my parents live in Kolkata. They do not get any water bill. Calcutta Corporation has now made drinking water free. If you make something free, people abuse it and disrespect it. So, the best way to go about water reuse is by charging whatever it takes to give that thing. If it costs you, I don't know in India what is the cost. But if it costs you 1 rupee per liter, I'm just saying, that's what you have to charge. Because if you make it free, then ultimately you are paying, but in indirect.
In this case, approximately 5 rupees per liter.
5 rupees per liter?
Some 5.
Oh,
In most of the
way
cases.
too high.
Suppose there is some treatment, small amount, and if you pay 5 rupees, they will do 1 liter or.
Kiosks at railway stations. That's what you said.
No, but that is not public water supply. Because if it is 5 rupees per liter, and you are looking at 135 liters per person per day, 135 times 5 is how much?
More than 700.
700 rupees per person per day, that's unbearable. And I mean, you can't run a public water supply now.
5 rupees for drinking it.
Pardon me?
5 rupees, I think, it is for drinking water.
Yeah.
That is to drink it.
135 electricity includes everything.
Yeah.
Drinking, everything.
Of course, but you have to supply that. And the question is, I don't know the number, but I'm sure there is a number. And it may vary among regions. In Rajasthan, it will be much higher than in
I guess the tax which is paid by municipal tax, that probably includes some portion of the water.
Yes,
Probably.
of course. But if you don't charge for it directly,
Yeah, exactly.
if it is hidden, then see, in economics we say that if something, the cost is hidden, then it cannot be the most efficient cost, because the moment you have it hidden, that means there are all these other factors that come. Any other question? Okay, so then we will move into our next topic, which is energy recovery. And please give me a couple of moments while I set myself. I need to bring in that PowerPoint file. But now in this file, we have a couple of links which are to YouTube videos. Will they work directly?
It's connected with the
Okay, wonderful. So now we will look at numbers in terms of, well, if we have a wastewater, or not necessarily wastewater, we can look at agricultural waste, which I will give you some ideas of. Because right now, a project that we are doing directly deals with it. So, but ultimately it will come to wastewater, but let's just see how we can look at in terms of energy component. Now, what this presupposes or presumes is that you have a working idea of anaerobic digestion. How many of you have taken a course which has dealt with this topic of anaerobic digestion or anaerobic treatment? Very good. So I will not go into the details, the acetogenesis or the methanogenesis. We will just primarily look at the energy component of it. Okay? But if you cannot follow a particular slide, please let me know, and I will be more than happy to elaborate on it. So, Upendraji, how much time do we have for this session? When should we stop? 45 minutes. Okay. So, what we will do is we will go ahead for the next 45 minutes or so, and then if there is still something left, we will do it in the tutorial. Okay. All right. So, I will skip these because these are all US energy consumption numbers, which don't necessarily help us understanding. Okay. So, when we are looking at energy which is non-fossil fuel based and non-wind or nuclear or solar, then the next one that comes in that list is biofuel. That means you take some biomass and you generate electricity out of it. And what are the common types? Well, that's both. They can be crops, and these crops can be like ethanol, for example, ethanol from corn. Garbage, because it is organic, landfill gas. When we have these municipal solid waste landfills, nowadays in the United States, it's compulsory that you make the landfill such, you design the landfill in such a way that you collect the gas. And then, of course, you harvest that gas. And alcohol fuel also. Skip this, I'll skip this, I'll skip this. These are all United States numbers, all United States numbers. Let me just mention one quick thing. Waste to energy. So, when we talk of waste management, then we talk of this inverted triangle or pyramid, and we say that we want to avoid this landfill because landfilling is the least efficient way or the most inefficient way of dealing with the waste. Okay? Because what you're doing is you're just kind of hiding it out of sight. So this is the last option, and among the other options, waste to energy is also pretty low, because what waste to energy is doing is you are converting it, no doubt about it, but you're not really using the material part of it, you're just using the energy. If you can reuse the material part of it through the 3 R's, as we call it, reduction, reuse, and recycling, they are much bigger. So, okay, let me just mention one more quick thing. When we say waste to energy, there are 2 types of energy actually. One is you burn this waste and you get energy in the process. And that's what we do in waste incinerators. We burn the waste at whatever temperature we have to, and you generate this heat because there is organic matter in the waste, and this heat you then trap. But the other side is what we call, in terms of anaerobic digestion, where it is also waste to energy, but it is much more efficient. You just burn the waste and try to capture the heat, get a very little amount of energy. If you can use it in a microbially mediated process like anaerobic digestion, you get much more energy. Okay. So I just wanted to make that clear. Yeah, let's get this. So when we look at biomass to biofuels, which is a very hot area, then you can start with municipal solid waste, the refuse as we call it, garbage. You can look at segregated organic waste, for example. More favorable would be food waste, because food waste has high energy content. And you can look at sewage, you can look at biosolids, you can look at manures. Manures happens to be a very powerful, very high energy component biomass. And I'll show you a video where they are trying to do that with dairy cows. And we now have, in a research project that we are doing, we now have some very innovative technologies which we can use for chicken agriculture based on poultry. We can also look at biomass crops that you are growing to generate fuel, like corn, for example, some grasses, and we can look at crop residues. But the idea is that you get, through some biologically mediated conversion, primarily we will talk of methane, but you can, in that same anaerobic digestion process, you can, and we will go through some of the points, if you smartly manipulate these pathways, you can force the biofuel, the biomass, to give you hydrogen instead of methane. And hydrogen happens to be a more usable fuel. We'll go through some of the reasons for that. Or you can go through the ethanol route. These are the most common ones. There are many other biofuels that you can get, biodiesel, for example, but we will not spend. Okay. So I'll just spend a little time on anaerobic digestion. And the end products, as you know, are methane and carbon dioxide. And of course, I'm not talking of the undesirable parts which you have to then use, like siloxane and hydrogen sulfide and ammonia. I'm just looking at the energy part. We will look at the ammonia part most likely here. Okay, so let us look at one video if everything works fine. Open the sound thing. Let's see if it comes up.
There's no fear of the dark at this farm in Eastern Ontario. That's thanks to power generated through the production and processing of methane gas. And there's a steady supply.
We knew how much energy is in manure from past experience here. We tried a bit in Switzerland to make heat out of methane gas. there is about 1.5 to 2.5 kilowatt hours per cow per day in well-fed dairy cows. So our consumer day is about 450 kilowatt hours, and with our animals, about 250 animals, large animals, times 2 kilowatt hours would be about 400 kilowatt hours. So we figured that we would be able to produce our power if the system would run well.
Paul and Fritz Clazy arrived in Canada in 1990, armed with a desire to be dairy farmers and to apply their technical knowledge to explore green energy. The Clazy brothers milk 140 head of cows and have 280 head of livestock. 6,000 cubic meters a year of manure is produced.
The manure comes out from the cow, goes into the garden. We run the garden twice a day, morning and night. The manure goes all around behind the cow. It comes up here. This incline goes down in a 3-foot pipe. It's no pump, it's gravity fed, and runs out to the digester.
The manure is stored for 28 days in the digester. Helpful bacteria naturally present get the process going until the manure is well fermented. Heat is essential to this whole process, especially given cool Canadian winters. The manure has to be kept at around 40 degrees Celsius to have perfect fermentation.
So what we did here on this farm, we tried to build a heat exchanger where we can exchange the warm manure who goes out from the digester with the cold manure who comes in from the barn. What we also do, we use from the milk cooling, we make hot water from the milk that we cool down. We have to cool the milk from 36 degrees down to about 2 to 3 degrees.
The fermentation process produces methane, nutrient-rich manure, and ammonia. Manure is comprised of between 40 and 60% methane, compared to natural gas, which has a methane content closer to 90%.
Rubber-sized top. On top of that, that works as a storage for our gas. So this bubble is like a balloon, goes up and down. We have a storage room for about 150 cubic meters of gas, if it's full or empty.
A full dome represents 250 kilowatt hours of power, which occurs twice a day, every day.
Manure is considered to be liquid gold by farmers, and that's doubly true for the Clazy brothers. As this dome drops, energy is directed to the Hydro One power grid, forcing their electricity bill down.
The valve has opened now, and here we lose now methane gas because the balloon is full, and we really should start up the generator. Here the methane gas comes into the generator. Here we measure the volume of the gas with a meter. And then we go in, up here to the turbocharger where the gas gets mixed with air, goes through the aftercooler of the turbocharger, and comes in here into the diesel engine.
This powerful system and some good negotiation has resulted in a net metering agreement with Hydro One for the Clazies. They feed the province's power grid when the generator runs and the farm's not using the energy produced. And here's something you don't see often, a hydrometer running backwards. Paul Clazy sees many pluses to the process.
One advantage is usage of the power. Another advantage which we really like is that during the summertime we can make the hot water in the houses, and we think largely we can probably heat the houses with the energy the heat which comes out of the generator. And a big part of all is the digestion of the manure, which really we like to see that the manure is much more available to the plants, and all the bacteria which E. coli and so on are gone in the manure.
The sustained heat also kills weed seeds, a big advantage for any farmer, reducing requirements for spraying. So it's value added to value.
We are a bit pioneers, I would say. We imported a lot of stuff from Europe. We put the system together here ourselves. We have some technical knowledge.
Paul has been able to put his experience as an inspector for Hydro Zurich to good use, combined with Fritzl's dairy farmer background, as they examine records of energy produced on site since the system's installation. They have reason to smile.
It looks good, but we have also other considerations. We spent some money on the system. We knew that the system will work. We're not exactly sure if we can come to a level of zero, but I think we will come very close to it.
Okay, so I mean, this is a very, very simple video. It doesn't go into the details of how much energy they are getting and how did they arrive at those numbers. But I just put it for two purposes. Just wanted to show you this video for two purposes. One is that even at a very kind of small scale dairy farm in Canada, which is basically run by two people, one can look at this kind of technology. And the other is this, what we call net metering or reverse energy generation. That means typically when we look at energy, we get it from the grid, we pay. Nowadays, in many parts of the world, including United States and Canada, if you generate electricity in your house, let's say from a solar panel, or in this case from an anaerobic digester, that electricity that you generate, you can give it back to the grid and you get money, because you are now generating this. And many utilities now have this mandate that they have to get to, let's say, in my state, they have to get to 20% renewable energy by 2020. Okay. And at present, they are nowhere near, they're about 12%. So they have this mandate, and in order to fulfill that mandate, they encourage people like me at a residence level to generate electricity and put it back into the grid. So this makes it much, much more economically, because in the past, what happened was, okay, if you generated electricity, you have to use it in your plant or in your dairy farm. And if you didn't use it, then it was waste. But now, when you are not using the electricity that you generate, you can put it back. That is very well. So, let's see a little more. This is anaerobic digestion, and these are pretty much all based on CHP, combined heat and power. So when we look at, I mean, it's a little thermodynamics is involved. We will not get into that. But the idea is, if you look at just electricity generation, you burn a fuel and you get some electricity. And again, when you go through the cycles in thermodynamics, typically, if you are looking at fossil fuel, then you have about, let's say, somewhere between 30 to 33% efficiency. So if you're burning coal to generate electricity, if the coal has 1 unit of energy in it, you are getting only 1/3 as electricity. Okay. Now, if you do a CHP, then you get a lot of heat, which you can now think of using sensibly. So in the video that you saw, they said, well, they use it to heat water. And hot water, as you know, is it has some economic component to it. I mean, that's why you install a geyser in your house so that you get hot water. that geyser, it runs on electricity, but the idea is that if you can supply heat or hot water, then you have a beneficial behavior. And we now have many successful projects where at a village level or a small town level, we have been able to show that if you do anaerobic digestion, generate electricity, when you generate methane, which you use to generate electricity, the heat part of it, if you can supply it to the household level, then you have a much better, what we call, return on investment. Because if you let this heat go away as waste, then your return on investment is very good. Okay, so all I'm trying to say is that the heat component now becomes also an important factor. So this heat that we are getting, then we need to now, once you generate the methane, you can use it in a variety of ways. You can use it directly into transportation. We now have the CNG, same principle as a CNG. In Kolkata, all the autos are CNG. In Delhi, in many cities in India, all these three-wheelers, they're all CNG. So you can use methane. Now CNG is natural gas, but methane is not necessarily, but more or less the same. So all I'm trying to say is you can use it in automobile, or you can use it to generate electricity. If you do so, then you have to look at what you do with the heat. Because if you let this heat go waste, then economically you are you're at a little disadvantage. Now, the other part is if you're looking at manure, for example, then at the end of the anaerobic digestion process, the biosolids that you generate, they also have a lot of nutrients in them. And you can then use it as soil amendment or things like that. So, in the tutorial, that's what I would like to do. I would like to look at the budget, the energy budget of a industrial wastewater. So, just the basics of the anaerobic digestion. If you start with the organic, that organic is typically in the form of a protein or fat or grease or oil or carbohydrate. So, these could be as polysaccharides. Then we go through the process of hydrolysis, where we convert them into monomers. And then we have these three pathways. One is what we call as the direct acetate pathway. So you take this, and this is of course all done by microbes. And this is not just one microbe, this is a microbial consortium. So one species in the consortium, they take this and ferment it directly into acetate. And then we go through what is known as acetate cleaving or acetic acid cleaving, where acetic acid is then partitioned into carbon dioxide and methane. So you have acetic acid, CH3COOH, and what you do is you cleave, and then what you get is methane plus carbon dioxide. So that is what we typically like to promote in our anaerobic digestion, that we go through this route because the end product is. Or, as I said, what we can do, what does happen in an anaerobic digester is there is one group that converts this monomer into hydrogen and carbon dioxide. And so, if I want, for example, my system to produce more hydrogen. Now, in a typical anaerobic digester, you do not produce hydrogen because you do generate hydrogen here, but then it immediately combines with carbon dioxide to give you acetate. And the hydrogen partial pressure is very, very low. But if you want to convert more of this monomer into hydrogen, you can smartly manipulate the system. cut off this pathway, and then you force this group of microbes to do all the work for you to get hydrogen. Now, what is the advantage? The advantage is that at least until about 10 years ago, a lot of people believe that we are moving towards the hydrogen economy because hydrogen is a very versatile fuel. So the idea was that if we could move into a hydrogen economy, then this would become very profitable. But for a variety of reasons, and we don't have the time to get into that, for a variety of reasons, hydrogen has not remained that much in its popularity. And now we are moving away from hydrogen, mainly into, again, back to materials. But what I'm trying to say is that when we study microbiology or environmental biotechnology, then when we study these pathways, we now have the capability to manipulate these pathways. That's all I'm saying. What end product we get, that is a different matter. But now we understand the microbial pathways so well that if we want, we can intervene and we can force certain reactions to happen much more so than the natural.
So it's for three processes. You need three separate reactors.
No, this is all one reactor. This is all one reactor. But of course, if it is a microbial consortium, then in one reactor you are getting a certain percentage of methane. If you want to change it, then you will have to manipulate some of the microbial species. When we talk of a digester, it is just one. But what we have seen is that if I split it into two reactors, in one reactor, the first one, I force everything to become acetate. Then I take this acetate, take it to the next reactor, and I do this reaction. Then my overall process efficiency is better. But that is a whole different discussion, whether to go one reactor route or two reactor route, because then you have to do a lot of other calculations as well. But in a typical anaerobic digester, all these things are going on simultaneously. And so there's acetate forming, which is cleaving. There is hydrogen forming, which is combining with carbon dioxide to again give you acetate, which is then cleaving. Then you have these short chain butyrates and the propionates, which are then again either go through the acetate route or through the hydrogen route. And ultimately, most of the hydrogen, almost all of it, is converted into methane. So what you get is methane, which is the fuel actually that you're looking for, because carbon dioxide, as you know, it is the most oxidized form of carbon, so it does not have any fuel. Now, what could be your starting materials? They could be brewery waste, which is what we will discuss in the tutorial. It could be dairy waste, dairy and cheese production, fish processing. I mean, I talked of aquaculture, where you are growing the fish. And of course, when you grow the fish, then you have to feed the fish much more than can transfer into the fish protein. So what we typically say is to grow 1 kilogram of fish, we have to put in at least 3 kilograms of fish feed. Now, what happens to all this remaining 2 kilograms? Well, you can try looking at anaerobic treatment to generate energy from. And you can look at some industrial wastewaters, for example, paper and pulp, something which is very, what we call high in COD, chemical oxygen demand. We can look at meat packing. Meat packing is very extensive in some parts of the US, where the main unique feature of meat packing wastewater is that it has very high protein, very high nitrogen, ammonia. And so, if you look at it anaerobically digesting it, then you not only get energy, you also can, if you can, pack the nitrogen in some fertilizer. That's so much the better. And with some If you have never seen a wastewater treatment plant, the smell may not be very agreeable, but from a satellite or from a hot air balloon, it looks very nice. And typically what you see are these clarifiers and the aeration tanks. And for those of you who have taken a course in wastewater treatment, you go through all these unit processes: the primary clarifier, the blitz chamber, the secondary clarifier, the aeration tank, and also all that. But we are looking mainly at the energy component of it. So if you look at the energy component of it, then what we typically see, and again, these numbers are not cast in stone, they are just to give us a guide, that from municipal wastewater treatment plants, the biogas is typically about 55 to 60% methane. And why is it that one can do those calculations? Which again, because of lack of time, we won't be able to. But it all depends on the scenario. What is the alkalinity present in the system? What is the pH? And if you then do a little bit of chemistry calculations, and if you do a carbon budget, you can see how much of it will be carbon dioxide, how much of it will be methane. You can do those calculations. But today we are interested in the energy part of it. And in the energy part of it, we have some guidelines. So, for example, typically use, and this is again in a unit that you are not very familiar with, British thermal units. But in the tutorial, we will look at in terms of joules, which is something you're more familiar with. And again, the volume that we use is feet cube, not meter cube. But what I'm trying to say is that we have this background information available. And now, when we look at the waste constituents, we can get a good feel, which we will do in the tutorial, of how much energy we have. And that energy we can use to generate power, and the heat we can supply as hot water or some other molten salt, for example. We can store heat nowadays. It doesn't have to go waste. And this slide shows the gas being flared, but nowadays we have moved away from these gas flares because flaring basically means you are wasting. We now have many ways to capture. And typically these digesters look this egg shell shape, as we call it, because of some particular reason. And it has a certain fuel value which we can look at, which we use to do. So in the tutorial, we will do some calculations. How many of you have a calculator with you right now? One. So please do those calculations with me, and for the others, please bring a calculator with you, because we will be doing similar calculations tomorrow and day after. But don't worry if you don't have it today, because I will give you all the numbers.
That is meat packing used for the.
Yes, meat packing.
How much solid content is there?
Oh,
Is the protein is in the solution form or is in the solid? The sludge.
It is difficult to answer because there is no one meat packing way. It all depends on the industry itself. But the solid form is typically captured as biosolids. So that is outside the purview of my discussion today. It is mainly the liquid form which we have to deal with. But most of the time, it makes it as a slurry. And in the slurry, typically, the ones that I'm familiar with are about, you can say, maybe maximum of 8% suspended solids. 8% is very high. I mean, 1%, keep in mind, is 10,000 milligrams per liter. So 6%, 7% is pretty common. But the hydrolysis of organic nitrogen to ammonia is very fast. So you are dealing with the nitrogen in the solution. So again, now this is something very interesting and very useful. Many people, for example, this is the slide that I have taken from University of Minnesota. They did a lot of work and they were then able to come up with these. So they say, if you have a dairy farm, okay, per 1,000 pounds of cow, I mean a typical dairy cow in the United States, what we call the Holstein cow. The Holstein cow, I think, is somewhere between 1,500 and 2,000 pounds. So, how much is it in kilograms? 1,500 pounds means 1,500 divided by 2.2, whatever it is. Let's say maybe 700 kilograms. 700 kilograms. Yeah, that sounds right. So, a typical dairy Holstein cow is 700 kilograms. And for every 1,000 pounds of its weight, it has 10 pounds per day of volatile solids. And if you anaerobically digest it, you get 39 BTU of biogas, which has an energy equivalent of 23,400 BTU. Again, BTU is a system of energy, a unit of energy that only we in the US use, but I will convert it into joules when we do the nuclear. But the point being that this kind of research has become very useful because now we can generate numbers very easily. If you have a big farm. Now in the United States, what has happened is that we have moved away from, let's say, individual farms, mom and pop farms as we call them, to these giant factories. These are basically factories where they produce meat or what that has done. These are called CAFOs. Combined animal farm operations. So these are, as you can see, these are factories, which means that the density is very high. In a very small piece of land, and I'll give you some numbers. In a very small piece of land, lots and lots of farm animals staying very close together. The chickens or the pigs or the cows or what. Now, what happens is if you want to maximize your meat production or your milk production, because these cows are staying so close to each other, there is always this danger that if an infection comes in, it spreads like wildfire. So you have to protect these animals from infection. How do you protect? You vaccinate them, you give them all kinds of antibiotics and all that, very high dose. And what is the problem? The problem then is that, well, milk now contains these antibiotics. The meat contains these antibiotics. So that is a whole different problem. But what I'm trying to say is that because of such charts, we can now very easily look at energy, which is what is my focus for today's session. And these are very conservative values. As you see, it says biogas production is typically much higher. And I will give you some values which we have seen in our lab, which are much higher. And again, without going too much into the thermodynamics, what do you do if you go through this cycle? This is what you saw in the video, that the methane is used as a fuel, and the fuel and the air are mixed in order to kind of run this turbine. Then you get certain value of energy. Or you produce something like this, which is also CHP, combined heat and power. See here the word CHP. I will not get into the details. Let's So now we have industrial scale units that work for all ranges of electricity generation. So if you have a big farm, you are generating a lot of methane, you can go for a higher generator. If you have a small farm generating very little methane, you can scale it down very easily. So, I'll just skip this. These are micro turbines, very useful. Again, because you can scale them up very easily. It was more or less about this slide. The natural gas hot water boiler, compressor engine. So I'll skip this. All right. So now, as I said, you get this methane through anaerobic digestion. You can use it to generate electricity, but you can also use it for transportation purpose. And I'll show you this slide if it works fine, which it should. And if the font is there, this one. Okay, so this is an article which I picked up. It says the city in Colorado. Colorado is a state in the United States. It says the city is fueling vehicles with gas produced from a wastewater treatment facility. And we will not read the whole article, we don't have the time, but I'll just read the first few lines. So this city, it's called Grand Junction. It has a wastewater treatment plant, and that wastewater treatment plant generates methane, and that methane is used to fuel the city's fleets and buses, and is available for public vehicles as well. And it then goes on to give you some numbers which we will not spend time on. And I will upload this so you can read it if you want. But what it's saying is that it has 400 to 500 gasoline gallon equivalents produced daily to fuel 37 city-owned CNG vehicles, resulting in the reduction of 3 million pounds of carbon dioxide. So, many treatment plants now throughout the world are looking at using the methane to fuel transportation vehicles. In this case, it is city buses. So, in that sense, methane is a pretty versatile fuel. So, now, when we look at methane, if we want to generate electricity, then today, rather than using a diesel generator, which is what you saw in the video, we can use a fuel cell. How many of you know what a fuel cell is? Fuel cell? Fuel cell. Okay. Fuel cell happens to be a reactor where if you are trying to generate electricity, it has much higher efficiency than the diesel generator or the coal generator. Why? It's a little bit of thermodynamics, which we will not get. But all I'm trying to say is that in the past, we were limited to maybe 33% of the heat generated as electricity. Now we can go maybe 40%, 45%. So 10% extra is pretty good. And when we talk of fuel cell, there are actually two types. Until now, or even today, you can say most of the ones that we use are what are known as MCFCs, molten carbonate fuels. And just to give you an idea of what a molten carbonate fuel cell is. So what happens is you bring in the fuel, okay, and then in a fuel cell we have these two electrodes, the anode and the cathode, and the anode basically to generate the electrons, which is the electricity that you are getting, but you also get this hydrogen, and the H plus that travels through membrane. It's called a PEM, proton exchange membrane, and then depending on, in this case, molten carbonate, you form molten carbonate by a combination of carbon dioxide and oxygen, and this molten carbonate comes in, and when it meets the proton, then you pretty much get the end product. Okay, so oxygen comes in, carbon dioxide leaves, the fuel comes in, and the fuel is oxidized at the end. That's basically what's going on. And the only problem here is that you have to run this system at a very high temperature. So molten carbonate fuel cells run typically at 600 degrees Celsius. So if you run it at 600 degrees Celsius, you can see that you have to spend a lot of energy to get your fuel to that temperature. Whereas if I do, and I am kind of running out of time, so I will not go to the direct methane fuel cell, but it just so happens that this direct methane fuel cell if you go to a direct methane fuel cell, it is even better. As of now, it's only been tried out at the lab. There's no commercial installation of a direct methane fuel cell, but the potential is very high. Okay. Typical question? There is a picture. I will show it to you during our deep dive. Efficiency, as I said, this is a little old slide. It says fuel cells have an efficiency of about 37%, but as you can see, the range is pretty high, 35 to 55%. The direct methane fuel cells can reach upwards of 50%. Capital cost, well, of course, fuel cell is more expensive. Capital cost, but no question about it. Gas turbines or diesel generators are. So this is about $3,000 per kilowatt. Gas turbine is even cheaper, whereas molten carbonate fuel cell is at least 3 times as much capital cost wise. But of course, as we discussed in reference to an earlier question, you cannot just look at this chart. You have to look at everything. How much, what is the increased efficiency you are getting? What is the price that you get for the electricity? I don't know. In the United States, we typically, when we do these calculations, we say electricity is 15 cents per kilowatt hour, which means, let's see, 15 cents per kilowatt hour is how much? 15 cents is $1 is 70 rupees. So 70 rupees means how much is 15? Does anybody has a calculator? If $1 is 70 rupees, how much is $0.15? 0.15 times 70?
10.5.
So rupees 10 per kilowatt hour. That is what we base our calculations in the United States. I don't know. Here, does anybody know how much you pay for the electricity per kilowatt hour?
It varies from state to
Varies
state.
from state to state.
Okay. Or low end?
4 to 6.
4 to 6 rupees per kilowatt hour.
In my experience.
So it's more or less comparable then. 4 to 6 maybe. So the point that I'm trying to make is that you cannot just say, oh, fuel cell is ruled out because it costs 3 times as much. Because this is the capital cost. And now you get the benefit of increased efficiency, which means you are generating more electricity, and that electricity you are selling, or that is the rupee price, let's say 4 rupees per kilowatt. You have to do those calculations. That's all I'm trying to say.
The capital cost is only initial cost.
So when we talk of expenses, we say capex, capital cost, and then the operation and maintenance cost, and then you get the return. So we do all those. This is something which we do in engineering economics. I don't know. Do you take a course in engineering economics here? BA-Tech. You do all those calculations. So this is the capital cost. This is the O&M cost, and now this is the revenue that I'm generating. And so based on the revenue that you generate, then you look at return on investment, how much time it takes to recover. So all those calculations, which we will not do, but so we can also look at microbial fuel cell, which is something which is very becoming very hot. But I think we have reached 3:45 and the tea is ready. So enjoy your tea and let's see. When we resume, which will be at 4 o'clock, we will do this tutorial one. We will do some calculations based on anaerobic digestion of an industrial waste. Okay? Sounds right? Good. Very good. So enjoy your tea. Okay, welcome back. Questions? Okay, so we will do a very short tutorial. I know it's been a long day for you. What I would like to do is just kind of give you a flavor how to do such calculations. We will not be able to do everything that I have on the screen. I will upload this document, but we will just look at the basics. That means how much energy are we looking at in a wastewater? How much of that energy can be captured as electricity? How much as heat? What do we do with the heat? Okay. So we will look at an industrial wastewater. Now, this is a brewery. In the United States, there are these so-called microbreweries. And microbrewery is basically a one-person, two-person, family-owned brewery where they produce beer. Beer happens to be very, very popular in the United States. Consumption is very high. And also, why only United States? In Europe, and I'm told increasingly so in India as well. So I don't think this is a very far-fetched example. But the point that I want to try to make is that brewery wastewater has some very unique characteristics, and let's just look at that. So the first thing to keep in mind is, of course, you are interested in the beer, you drink the beer, but from our perspective, from an environmental engineering perspective, the fact, the important thing is that 1 liter of beer that you produce generates as at least typically 10 times as much of wastewater. Okay? Because if you look at the typical beer production process, this is the price that you pay. So if you are generating 100 liters of beer, you are generating 1,000 liters of wastewater. Okay. But that's not everything, because when we say wastewater, I'll show you a graph that I'm sure you have seen before in some form or another. When we talk of municipal wastewater, then of course you can't just put one number, it's a range. And when we say typically in the United States, municipal wastewater, the one that goes into a centralized wastewater treatment plant, it has solids, total solids. You can say, and again, so you see there are 3 columns here, weak, medium, strong. And we are looking at solids anywhere from 350 to 1200 milligrams per liter, out of which dissolved solids are total dissolved solids, TDS, at 250 to 8. And these are just guidelines. These are not hard and fast numbers. I picked it up from the most widely used wastewater treatment plant design book, the one by Chopinoglis. Then you look at what are the fixed solids. Fixed, as you know, it means inorganic. Inorganic solids, somewhere in this range, 145 to 525. Volatile, 105 to 325. Suspended solids, 150, so forth and so on. But for our purposes, perhaps the most useful information is that if you're looking at a municipal wastewater, the chemical oxygen demand is somewhere between 250 and 1,000. And the BOD is somewhere between 100 and 200. And when we say BOD, of course, it's always BOD 5, as you know. Okay? So this is typical municipal wastewater. Now, if you look at brewery wastewater is much, much stronger. Also, well, the COD now is somewhere 2,000 to 6,000 milligrams per liter. Compare it to 250 to 500, let's say. So many times stronger. BOD, again, BOD 5 is somewhere between 1200 and 3600 milligrams per liter. BOD 500 to 400 milligrams per liter. So the point that I'm trying to make is that it is much, much stronger. When we say stronger, it means it has much higher organic. Now, and it does have some nitrogen and phosphorus. We will not talk about it today. We will talk about it in our next tutorial, which is tomorrow. The phosphorus part, and the day after tutorial will be the nitrogen. So today I'll just look at the energy part. The thing is, if you have such a strong wastewater, then you can't really just put it down the sewer line and transport it to the wastewater treatment plant, because it will stress your sewer line. Because typically, as you know, from the point of collection, the wastewater may have to travel miles until it reaches the treatment plant, and it may be hours, 6 hours, 8 hours is pretty common. So if you put this wastewater in your sewer, and if it takes 8 hours to reach the treatment plant, what is most likely to happen is that the microbes present in the wastewater, they will start acting on it, and very soon this will go anaerobic. The sewer will go anaerobic, and you have all kinds of problems. You have water problems, you have safety problems. I mean, even today, you will not believe it, we get multiple deaths due to sanitation workers entering the sewer manhole without adequate safety protection, and they don't anticipate any methane in the system or any hydrogen sulfide in the system, and they go in, and then there are fatalities, there are serious health problems, so forth and so on. So the point that I'm trying to make is, it's not a smart idea to just send it to the wastewater treatment. And that is also a perfect opportunity for us to do it, to put this through an anaerobic process at the site. So that is what we will be doing over the next half an hour or so. And total suspended solids is not very high, but they do have a much higher organic. Okay. So, in our case, and I will write these down for you. And because we have a very limited space here, I may have to erase these things. So please do copy of whatever is on the board, because it will not remain very long. So in our case, our production and production is always in terms of the beer, of course. The production is 7 million bottles per year. This is the example that we have. 7 million bottles, and that translates to 3.3 billion liters of beer per year. So in 1 year, you are producing or you are selling 3.3 million liters of beer. Okay, that's the production rate. But as I said, for every liter that you generate about 9 to 13 liters of wastewater. So today's purpose, beer is not our main focus, as crazy as it sounds. Our interest is in the wastewater. Okay. So these calculations are based on 11 liters of wastewater produced per liter of beer. And so our wastewater production rate, wastewater generation rate is 36 million every year. Okay. So these numbers have been given to us, and this translates to approximately 100,000 liters per day. I mean, in design, we approximate because these numbers aren't really very sacrosanct. They're just relative. So, 36 million liters is 100,000 liters per day. Okay. Now, when we look at anaerobic digesters, typically they have a diameter of 6 to 34 meters. These are all US numbers. I don't know comparative Indian figures, but I suspect they will be the same. Digester is a digester, so not much. I don't think Indian digesters are very different in terms of their range and geometry and height is 6 to 12. Now, digesters, as you know, do have a bottom slope to collect the biosolids. Have a diagram. And you may not be able to read all this. It's not very important. All I'm trying to say is that they do have this bottom slope. Select this line. And that bottom slope, and these are all typical numbers. You may find something a little different, but typical numbers of a bottom slope are 6 units horizontal, to every 1 unit per. And these are given by design parameters. Okay. Not that it is very important for us, because we are not designing the digester, we are just sizing it. Okay? And in our case, for this waste border, the COD in means into the digester. The COD coming in is 4,000 milligrams per liter. COD out is 400 milligrams per liter. That means the digester is operating at 90% efficiency. It's able to remove 90% of the COD. And so the COD destroyed is the difference of 3,600 milligrams per liter. Again, these numbers are all given to us by the microbrewery. We have no control over it. Okay? Questions?
Is there any retention time or time?
We'll get to that. We'll get to that. Just hang on for a moment. Okay. Now, again, typically for anaerobic digesters, the detention time was the question asked, is typically I would say 15 days to a month. Let's see. Yeah, typical detention time is 15 days to a month. 15 to 30 days. You know, the digesters, they typically run at 3 temperature ranges. There is something we call mesophilic digester. Mesophilic digester typically runs at about, you would say, 35 to 37 degrees Celsius. Then there is a higher temperature called thermophilic. Thermophilic digesters run, you can say, about 43 to 45 degrees Celsius. And then there is cryophilic, which is not very common, but we do have some cases. Cryophilics, they run, I would say 25 to 27 is the most common. Now, it so happens that the typical microbial species that you get in the digester, their cryophilic version, they are not very efficient. So, cryophilic digesters, they don't produce a lot of methane. So, we will run a mesophilic digester, which will be run at about 37, I think. Let me just see, I think, yes, we ran this at 37. Yeah, 37. So we ran it at 37 degrees Celsius. So that's mesophilic. In our case, the digester 37 degrees Celsius and detention time is 20 days. Okay. Questions? All right. So for those of you who have a calculator, can you tell me what is the volume of digester that is required? So you have a flow rate of 100,000 liters per day, detention time of 20 days. So volume of digester required would be 2,000 meter cube, right? 100,000 liters per day times 20, and we will use 4 identical digesters. So we will use, and of course, when you say we will use 4, you have to provide for a realistic purpose at least 5 reactors, 1 being there. So our calculations would be on the basis of 4. So 4 reactors which are placed in series and they run in parallel, and each digester will have a volume of at least 500 meters. Okay. Questions? Very straightforward. Now let's size the digester. If I take a 10-meter diameter, then the height would be about 6.5 meters. And so I will use 4 digesters, each with a diameter of 10 meters and a height of 6.5 meters. And if you want to cross-check, please do so. Pi by 4 t square h should give you 500.
between height or diameter, which one is the most important factor?
Diameter.
Diameter.
But you have the range. As long as you are in this range, you are fine. So, do the calculations seem all right? 10-meter diameter, 6.5 meters height. Does it give you 500 meter cube? More than 500 meter cube of volume? Yes. Okay, very good. As you know, in design, we always kind of round it up. So, if you want to look, an isometric view would look something like this. Side view would look something like this. Up view, and this is how you will have the system. Central manifold coming in, then it being diverted to 4, equal of course, and then so now we have to do one very important calculation, and that is what is the relationship of COD with methane. So we know how much COD we are removing, 3600 milligrams per liter, 100,000 liters per day. How much methane does it translate to? That calculation, the chemistry behind that calculation is very, very important. So let's just do it step by step. Okay, so you all know the definition of COD, right? Chemical oxygen demand. So it is how much carbon you have, and in order to completely oxidize that carbon, how much oxygen do you need? That is the idea. Has anybody done a COD experiment in the lab? Any of you done that? Remember, what we do is we take our wastewater, which has the organic carbon, we put very strong oxidized agent, put potassium dichromate, and then we put pot of acid, and then we boil that. And under these conditions, there is no way you can have any reduced carbon. It is completely oxidized. And so what happens is that you take excess potassium dichromate. So in the COD experiment, the organic matter is oxidized to carbon dioxide and water, and oxygen is not oxygen, chromium 6+ hexavalent chromium is reduced to chromium. And you know from principles of equivalence how much chromium you use, which means how much, we basically look at how much chromium is remaining, which means how much chromium was reduced, and you can then relate it to how much organic matter. So the basic equation is very straightforward, that if I have organic matter which is oxidized to carbon dioxide, then how much oxygen do I need? Well, that gives me the COD part of it. And if I convert it into methane, so how much is the COD of methane? That is what I'm trying to do now, COD of methane. And you can write this balanced chemical equation very easily. That 1 mole of methane needs 2 moles of oxygen. This is 16, and this is 64, right? And so COD of methane, 4 grams oxygen per gram of methane. Agree? And so now we can correlate this. Excuse me. 1 kilogram or 1,000 gram of COD complete metabolism of 1,000 gram of COD will produce how many grams of methane? Can you tell me? 1 gram of COD is 4 grams of oxygen. And so 1,000 grams COD will be in order to oxidize the organic matter, I need oxygen. And that oxygen is the oxygen demand. And the oxygen demand of methane is 4 grams oxygen per gram. So for every 4 grams of COD that I need, I get 1 gram of methane. So this will be 250 grams, right? Agreed? So if I can oxidize 1 kilogram of COD, I will produce 250 grams of. And so because we have to convert mass to volume, we need moles, PV equals nRT, the ideal gas law. So 250 grams CH4 equals 250 over 16 moles of CH4, which is 15.65. So every 1,000 gram of COD that I reduce gives me 15.625 moles of methane. Okay. Questions? All right. Then volume of 1 mole of methane at STP is how much? Ideal gas. We consider, of course, everything to be ideal here. So 1 mole of an ideal gas, how much volume does it occupy at STP? 22.4 liters. That is something we have seen in chemistry 22.414. Okay. So total volume of methane produced equals 22.4 liters per mole times 15.625 moles, which comes out to 350 0.35 meter cube. So every 1 kilogram of COD will give us 0.35 meter cube of methane. That's the idea. Okay. All right. So in our case, COD destroyed equals 3600 milligrams per liter times 100,000 liters per day. That comes to 360 kilograms. Because we have 1, 2, 3, 4, 5, 6, 7. 10 to the power of 7. And we know 10 to the power of 6 milligrams is 1 kilogram. So 36 times 10 kilograms per day. Right? Agreed? We are destroying 360 kilograms of COD per day by converting it into methane. And we know that 1 kilogram gives us 0.35 meter cube. So we can very easily calculate how much methane volume we are producing. Methane produced is 0.5 meter cube times 360 and mass of methane. So this is per day. Mass of methane produced is, sorry, not mass, moles. Moles of methane produced is 15.625 moles of methane for every kilogram, but we have 360 kilograms. So 15.625 times 160 per day, which comes out to 5625 moles. So every day we are generating 5625 moles of methane. Questions? Questions? Yeah.
Here you use the only stoichiometric equation, only methane and oxygen is there. Suppose in my it is a heterogeneous system, so methane maybe or maybe any other system, glucose also may be present. So at that time, what I will do? With stoichiometric equation.
Glucose will also be converted to carbon dioxide. So as long as it is being completely oxidized, it doesn't really matter what you're starting. because we are looking at the oxygen equivalence, oxygen demand. So we didn't even know what is the constituent of this brewery waste. It's not really important. As long as we know the oxygen equivalence, we are fine.
So suppose I'm saying that, suppose that I have some equation, first order equation, CH4 plus oxygen equal to something on first order equation. Suppose in another organic material is there is suppose 3 or 4 reactions taking place. Then I can calculate individual COD and I prefer the most low.
No, we don't calculate individual COD. When we have a wastewater, that is something which is a difference between an environmental engineer and a chemist. Chemists look at compounds, they look at concentration of compounds. We don't have that luxury. I mean, we were talking of meat packing waste, we were talking of paper and pulp waste. I mean, so many kind of varieties of waste we get. What individual constituents are there, we don't have the luxury. I mean, if I have to do an analysis, it will take me days and thousands of rupees. I don't have that luxury. And nor do I really need it. Because I'm basing everything on the premise that it is being oxidized to carbon dioxide. So as long as that holds, it doesn't matter what the original form is. So that's why I'm saying COD in is 4,000, COD out is 400. The COD out of 400 most likely is recalcitrant organics, which anaerobic bacteria cannot really. Okay, so now we need what is the heating value of methane. Methane is the fuel. So we go to Handbook of Chemistry and Physics and we get that the low heating value of methane is 875 kilojoules per mole. And we are producing so many moles per day, so heating value, or I shouldn't say heating value, I should say energy, because it's not just heat, this is more energy content. So energy content of waste in that anaerobic digestion process is 875 kilojoules per mole times 5625 moles per day, and that comes out to 5 billion kilojoules per day. Okay. So that is the amount of energy I have in my off gas, 5 million kilojoules per day. Now, what am I doing with it? Let's say I want to run a diesel generator. That means I want to generate electricity. So if I want to generate electricity, and so I did the calculations based on a fuel cell. So if I run a fuel cell, so with this energy content, I just put it into a fuel cell. And this is an MCFC, molten carbonate fuel cell. That's the most common one. So fuel cell, and in this case, the efficiency that I have, which again, based on people who have done work with this kind of wastewater, they say it's about 40%. So electricity generated, so 40% of this energy is now in the form of electricity. So electricity generated is, and I do this calculation because we are running short of time. I have already done this for you. It's 556 kilowatt hours per day, because this one was in terms of kilojoules. So you know, a joule is, I mean, 1 watt is 1 joule per second. So 1 joule, if I take 1 watt times 60 seconds per minute times 60 minutes per hour, I can then get kilowatt hour in terms of joules. And when I do that conversion, I get that electricity generated is 556 kilowatt hour per day, and heat generated is 834 kilowatt hour. As I said, when you run a cell or when you run a generator, you get electricity, but you also get a lot of heat. And in this case, the heat is about 60%, the electricity is about 40%. So I'll wrap up because I know it's been a long day for you. Basically, what I'm trying to say is that this electricity that you generate, of course, now you can put it back into the grid, you can use it for whatever other electricity needs you have in your plant, the brewery plant. That is outside the purview of our discussion. The heat that you get, what do we do? Well, we do need part of that heat to warm up the incoming wastewater. And we also need, in this case, the system that I have, it is running at 37 degrees Celsius. That's the mesophilic digester. But the outside temperature is 19 degrees Celsius. So this is kind of a little, you can say, spring or autumn. So because the outside temperature is 19 and the inside is 37, heat will flow out. I mean, so we need to protect this digester from all those heat losses. And what are the heat losses? There's a whole bunch of them. We will not get into individual, but I'll just give you the list. So you have heat loss of the floating roof, you have heat loss of walls with the wet soil, you have heat loss of walls with dry soil, heat loss of floor, and so you have to add them all up. And in this case, what happens is when you add them all up, you get a total heat loss of 621. Because of this difference in temperature. And of course, you have to do the best in terms of insulation and all that. But those are minor calculations. We are mainly interested in the electricity part because that's what is useful energy. As you know, when we talk of energy, there are all types of energy. There is good energy, useful energy, and then there is heat. Heat is the lowest form because heat, as you know, we cannot convert. I mean, if you go to second law of thermodynamics, basically says that all forms of energy can be converted into heat, but heat cannot be converted into electricity 100% efficiently. So, in this case, you have this much of electricity that you're generating, whatever use you may use, that's up to you. And you do have a little bit of heat left, which typically you would use to heat the water. And that hot water, if you need it in the plant, which again, we don't know in this case, it's outside the purview of our discussion, and use it for that. So I know we were supposed to end at 4:30, but anyway, so I will upload this document and you can go through each one of these calculations. But I just wanted to give you a basic idea. Yeah, I think I'll stop here because the rest is little more details which we didn't get into. In terms of details, what do I mean by details? Well, if you want to run an anaerobic digester, I'll just show you one diagram and that's where we will end. Okay, that's a different one. So let me just show you one diagram and that will give you a very good idea of what I mean. Okay, this is the that I wanted. You have to reduce the okay, I think this is good enough. You see, when you run a digester, there are some variables that you have to look at. One of them, of course, is the pH. pH is so important. And it's important not just in an anaerobic digester, it is important anything that we have to do in terms of chemistry. So pH, now it so happens, and this graph proves, that you want to run your digester at a pH of, let's say, 6.8 to 7.4. Why? Because only in that window of pH do you have stable reactor. What do I mean by stable reactor? You see, carbon dioxide is present in your off gas. So carbon dioxide, of course, has solubility. We know Henry's constant. So the carbon dioxide that is present in the off gas, that will come into some equilibrium with the solution. And in this pH, as you can see, if you're looking at alkalinity, it is all bicarbonate alkalinity, right? So you need, you can say, a minimum of somewhere in this range of bicarbonate alkalinity, so that you maintain your pH within this window, which is the stable reactor window. And in that window, if I know what is my alkalinity, if I know what is my pH, I can do very simple aqueous chemistry calculations that will tell me what percentage of carbon dioxide is in the off-gas. So I assume that it is 60% methane, 40% carbon dioxide. And so if it is 40% carbon dioxide, if my pH is 7, let's say, I'm just saying, then I would have to maintain so much of bicarbonate alkalinity in the system. If I don't have that much alkalinity, then what do? I will have to bring in some alkalinity from outside. So it's common in digesters that if they start to go sour, that means if they lose alkalinity, I have to add sodium bicarbonate or something like that from outside. So those are operational details which we didn't get the chance to get into. But the point that I'm trying to make is that you can combine your knowledge of aqueous chemistry and microbiology and biotechnology to come up with a very elegant, sustainable process whereby you have this organic matter in your waste, right, which is why you're calling it wastewater. And as Dr. Kumar said in the morning, there's no such thing as waste. And now you are, by your knowledge, you are converting it into energy, electricity, and heat, and you're also treating the water. Okay? So with that, we will end today, unless you have questions. Questions? So today's pace, how was it? Was it too fast, too slow, just right? If you're too shy, it's difficult to get an answer. Say that again? Obviously fast. Okay, why obviously? This adverb obviously is very dangerous.
Amount of time in the morning.
No, obviously fast also may mean that, well, if it is Professor Sengupta, it is automatically it is fast always. So that can also